Unit 2, Lesson 5 is about instantaneous rates of change, and in particular, we're going to use one of the more common versions, and that's talking about position, velocity, and acceleration. So hopefully by the end of this, you can find velocity and acceleration of a particle given a position equation. You should already be able to do that with an average rate of change, but you'll also be able to do that with an instantaneous rate of change. And also, if you don't know what velocity and acceleration are in particular, we'll cover that. So just a note, in calculus AB, we deal with one-dimensional motion. So just things moving up and down, as in, okay, so you have a rock, and the rock is launched upwards, and then it comes straight back down. Or maybe a common one is we would have a particle moving along the x-axis. Now, neither of those are particularly useful all on their own. But if you can get a really good grasp of the concepts of position, velocity, and acceleration in one dimension, then you can easily generalize into 2 and 3 dimensions. So just in terms of a definition, velocity is the rate of change of the position of an object with respect to time. So I say think speed, which is not quite correct, because velocity is kind of like how fast something is going with a direction. Like we said, one-dimensional motion. So it's like the speed in the positive direction and the speed in the negative direction, but not quite correct. So the way we write that, or a way to think of that, is the change in position. That's the Greek letter delta. The change in position over the change in time. So if we're thinking average rate of change, that would be like, we usually use S for position. So position minus over the corresponding times being subtracted. That's what we mean. And so maybe an example there. So the position could be 3, like the 3-mile mark, minus the 5-mile mark. And that would be a change in position of negative. Wow, that's some bad subtraction. That would be a change in position of -2. Divided by 2 is -1 mile per hour. As in, the velocity is 1 mile per hour in the negative direction. So you just kind of have to watch out for velocity. Okay, so in terms of just definitions and derivatives, velocity, well, let's go back here. Remember, or if you were in my class, remember, if you've never seen this before, ds over dt, that's kind of like delta s over delta t, but the positions and times are so close together, as in like when we're doing a derivative, it's like 2 points are right next to each other or almost on top of each other so as to basically be the same point. So very similar to delta s over delta t. But definitely not equal. And another way to say that kind of formal derivative, velocity, is, well, you should recognize this as the formal derivative. And of course, that's the position at some time. Well, let's circle some stuff because I don't know if you can see. Ooh, I think if I use my mouse. So the position at time t is our second position, and the first one is the position at that time t plus delta t. So we could think of, okay, we have a position graph. We have 2 times t, and that same t plus some change in time. Be better if we had a different color here. And so it's like we're starting off with the slope between 2 points, or an average rate of change. And as you can see, we're going to shrink the distance, delta t, down to 0. And by the time we're done, well, we won't have slope at 1 point, but t and t plus delta t are basically on top of each other. So we have an instantaneous rate of change. And a thing to watch out for, velocity can be positive or negative. If the change in position is positive, then velocity is positive. If change in position is negative, velocity is negative. We'll get to some examples. Another definition, acceleration is simply rate of change of velocity of an object with respect to time. And so we can think of that as velocity minus velocity over time minus time, much like velocity is a change in position over a change in time. And so hopefully that's not a big surprise that acceleration is the derivative of velocity if we're thinking in an instantaneous way. So we could do acceleration is that formal derivative of velocity. And so if acceleration is the first derivative of velocity, and velocity is the first derivative of position, then acceleration is the second derivative of the position function. And so just down at the bottom, maybe that'll make sense, but probably it would be better to do it with example. Acceleration can be positive or negative. When we're talking colloquially, we say deceleration, and we're not going to say that. We're just going to have a positive acceleration, meaning if the numbers get larger, and you have to be careful there, 1 second. If the numbers get larger, that's a positive acceleration. If the numbers get smaller, then that's a negative acceleration. So for example, just because it's a common misconception, 4 to 8, everybody would agree if the velocity was 4 and then the velocity was 8, that's we added 4, whatever the units are of velocity, miles per hour, meters per second, whatever it is. But going from -5 to -3, that counts as an increase in velocity as well, because that's adding 2 miles per hour, meters per second, whatever the units are. People just get a little bit confused because they think, -5 is farther away from 0 than -3 is. And that's not about velocity. That's actually about speed. So you just have to be careful there. Okay. So if you can memorize these 3 derivative statements, then, well, the new calculus knowledge with derivatives here is just going to be so much easier. So the first derivative of position is velocity. That's the first thing you need to know. Okay, so if you just think, okay, if I have position and I need velocity, I'll do the derivative of position. Cool. The next statement you need to know also starts with the first, and it's derivative again. So the first derivative of velocity is acceleration. And then we already saw this before, and this one is also about acceleration, but it's not the first, it's the second. And so if the first derivative of position is velocity, and the first derivative of velocity is acceleration, then the second derivative of position is acceleration. And I know it's a lot of words at first here, so let's get into doing some stuff. Okay, that is the wrong color writing, so I'll have to change that. So speed is just velocity without sign. In one-dimensional motion, it's really easy because you can just do the absolute value of velocity. As in, if the velocity at 2 was -3 miles per hour, then the speed at 2 would be 3 miles per hour. Total distance traveled is pretty straightforward. That means exactly what it sounds like, the total distance a particle travels. Displacement is a little bit weirder. So let's say there were 3 things on the same street. There was Costco, there was Trader Joe's, and there was a school called Ayala, which is where I teach. And they were all 1 mile apart, which is not quite correct, but we're going to simplify the math. And I just wanted these to have kind of a little bit stranger numbers. So it's like mile marker 2, mile marker 3, and mile marker 4. You can think exit signs on a freeway, that kind of thing. So if we start at Trader Joe's and then we drive to Costco, that's a displacement of -1. Because what we're saying is you are 1 mile in the negative direction from where you started. The total distance traveled at that point would be 1 mile. Okay, and then if we went from Trader Joe's to Costco and then drove to Ayala, well, this blue line, the length of that is plus 2 miles. And so you could think of that. Well, total distance traveled so far, well, we drove 1 mile from Trader Joe's to Costco and 2 miles from Costco to Ayala. So the total distance traveled there is 3 miles. What's the displacement? Well, there are 2 answers to that. For this blue line, which I'm covering up in yellow. For this blue line, the displacement for that is 2 miles. But since the beginning, our displacement is +1, as in we started at Trader Joe's, now we're at Ayala, that distance is +1. Okay, let's erase all that because it's getting confusing. And so let's think of the whole travel. We drove from mile marker 3 to mile marker 2, Trader Joe's to Costco to Ayala, and then back to Trader Joe's because we forgot milk. What's the total distance traveled there? Well, that was -1 plus 2 and -1. Our total distance traveled, we think of each of those as positive, so it would just be 1 plus 2 plus 1. We traveled 4 miles. What about the displacement? Well, displacement is a measurement of where you are compared to where you began. So if we began and ended at Trader Joe's, our displacement is currently 0. I made a companion video that's a little bit sillier for the same scenario that you may want to check out. It's a little bit more animated. It's not great, so don't expect much. So speeding up, we kind of know what that means. We use that all the time. And a good way to think about speeding up is getting farther away from the situation of being at rest. So I'm just going to think of everything as kind of on a number line, where over to the right is positive and on the left is not positive. On the left is negative. So this girl is running to the right, which means her velocity is positive. The wind is blowing her or like pushing her more to the right. So we're going to think of that wind as an acceleration, a force acting on her. And so if you were running and then the wind was at your back, you would be speeding up, right? You would be getting faster. You have to imagine the wind's really fast, so it's kind of pushing you. But it's more like the acceleration and the velocity are going in the same direction, so you'd be speeding up. Now, if you were slowing down, well, let's see, the girl's running to the right. That's a positive velocity. The wind is blowing in her face, or the wind is blowing to the left. We're thinking of that as a negative acceleration. We're going to call that slowing down. It could also be, well, is there another way to speed up? There sure is. If you're running to the left, that means velocity is negative. And if the wind is blowing in that same direction, the acceleration is negative. And that's the first scenario we started with, just with different signs. So velocity is negative, acceleration is negative. Those two are working together. The girl or you, whatever, are going to speed up. Likewise, the last scenario in one-dimensional motion. What are we thinking here for the sign of velocity? Well, she's running to the left, so velocity is negative. And the wind is blowing to the right, so that, I thought I had it here. So this is velocity is negative. The acceleration is positive, and she'd be slowing down. Maybe we can simplify that. If the sign of velocity and acceleration are the same, that would be speeding up. If the sign of velocity and acceleration are opposite, that would refer to slowing down. Okay, so I want to give you a little bit of meaning, kind of what things mean so we can translate what's going on. So the height of a rock is given by 3. And by the way, that 3 is the initial height. As in, if we did h evaluated at 0, we would get 3 plus 0 minus 0, whatever. So the initial height of the rock is 3. And, because this is a -16, we're talking about feet. Because for things near the surface of the Earth, this is, -1/2 acceleration times time squared. And the acceleration due to gravity is 32 feet per second, which I'm going to try to show you. This is initial velocity times time. So the initial velocity is 135 feet per second, which means we're not throwing the rock, we're shooting it out of something that shoots things really fast, and that is the initial position. So really height above the ground, which I should have typed the height of a rock above the ground, not the height of the rock if you measured, the bottom of the rock to the top of the rock. Anyways, so I've evaluated this height of the rock above the ground function at a bunch of places. And we can see at time equals 0, the height is 3. At time equals 1, the height is 122. That went up really quick. At 2 seconds, the height is 209. At 3 seconds, the height is 264. At 4 seconds, the height is 287. At 5 seconds, the height is 278. So average velocity should not be a problem. If it's average velocity from time equals 3 to time equals 4, that's an average rate of change, which means we're just going to do, and you might be thinking we're doing velocity, but we're not, because a change in position, which a change in height is, over a change in time gives us average velocity. I'm not really worried about the numerical value here. We're more worried about how we would calculate these things, because you should be able to just, I don't know, do that by hand, punch into a calculator, whatever we get. Well, let's think about when the rock was at its highest point. And you might be a little bit confused because we can't quite be certain. We know the rock is not at its highest point between 3 and 122 feet. We can see, and we kind of know about rocks, this increase, and then, well, from 287 feet to 278 feet, that's a decrease. But it could be the case that the rock hits its highest point between time equals 3 and time equals 4, or between time equals 4 and time equals 5. Because, well, 264, I don't know, let's say is right here, 264 feet. And we know 278 feet is up here. And we know 278 feet is below that. But we don't know if the rock went above 278 and then came down. The rock hit 278 on the way up and then came down later or something like that. So we know it's somewhere near the 4-second mark. Unlikely to be exactly 4, but somewhere in there. Okay. I probably should not have had those. But, well, let's look at this. So the height, the velocity, and the acceleration. Remember, velocity is the first derivative of position, and this height is a position, and the acceleration is the first derivative of velocity. So in between 3 and 122 feet, you know, the change in time of all of these is +1, which is nice because we can just think of, well, this is 119. And it's feet. But, well, that's a little bit weird. And then 122 to 209 feet, that's going to be a change in position, change in position, change in position. But what you'll notice, the velocity column is not average velocity, which is why these don't match. What we're saying is, at the instant, time equals 0, the velocity is 135 feet per second. But at the time equals 0.1, the velocity would be slightly less. At velocity time equals 0.2, the velocity would be slightly less. Okay. But what I really want to focus on is the change here. So velocity is measured in feet per second. And 135 to 103, that's actually a loss of 32 feet per second. Okay, and how many seconds did that take? Well, it took 1 second, which is why we get this unit 32 feet per second per second. And I like that better than 32 feet per second squared, which is fine, but I think it hides a little bit of meaning, as in, how much did the velocity change? Well, that was a change in velocity of negative 32 feet per second of velocity, and a change in time of +1 second. What is going on? And near the surface of the Earth, we pretend that acceleration due to gravity is constant. So you can see that's another change of negative 32 feet per second of velocity, negative 32 feet per second, negative 32 feet per second. And then on the way down, notice things are speeding up. The rock is gaining negative velocity. Okay. So same scenario, just so we can get an idea here. The height of the rock above the ground, again, that'll change when I retype this, is that same equation. Initial height of 3, initial velocity of 135 feet per second times time, and 1/2 of 32 times time squared, and t is measured in seconds. So how would we find the velocity of and the acceleration of the rock when time equals 3 and when time equals 6 seconds? Well, velocity is the first derivative of position. Height above the ground is position. So the best thing to write first is velocity is h prime of t, because you're saying, hey, look, I'm trying to find velocity. I'm doing it by finding the first derivative of this given equation. That's a pretty easy derivative. The derivative of 3 with respect to time is 0. The derivative of 135t with respect to time is 135. And the derivative of negative 16t squared is negative 32t. And so if we want the velocity at 3 seconds, we just put 3 in for all the t's, evaluate, and we get 39 feet per second. I know it doesn't say feet per second in there. That's kind of knowable, but you'd be given those sort of things. Okay, so should we do, well, let's do acceleration next. So what's acceleration? Acceleration is the first derivative of velocity. So we'll just write that. Hey, I have a velocity function. I'm about to take its first derivative. Acceleration, apparently at any point, is negative 32. And by the way, this is feet per second, each second. And so the acceleration at time equals 3 is negative 32 feet per second. We always want to give units if we can. So should we redo the calculus part for finding velocity and acceleration when time equals 6? No. We're just going to say, hey, the velocity at 6, substitute in 6, evaluate, negative 57 feet per second. And we already know that acceleration is a constant negative 32, so we can just say acceleration at the 6-second mark is negative 32 feet per second. So the next thing we want to do is find the height of the rock at its highest point. We kind of talked about that earlier. And the velocity of the rock at the highest point. And if you think about that, if you think about rocks going up, the second question is actually easier to answer. So this rock goes up, comes straight back down. The velocity of the rock at its highest point is kind of knowable, thinking about an intermediate value theorem thing. So on the way up, the velocity of the rock is positive. And on the way down, the velocity of the rock is negative, which means at the highest point, the velocity of the rock is 0. So we're going to do that first. So velocity of the rock, we already had that. I don't know why I'm erasing these. I just like things clean. The velocity of the rock is, we're just going to say, hey, we'll set that equal to 0. And you'll see in a moment, this is actually a calculator problem, but we can easily do that by hand. So how do we translate the meaning of what we found? Well, what we found is, the rock got launched upwards at time equals, well, again, we knew that was going to be about 4 seconds, 135 over 32. The rock is at its highest point. That's when the rock stops going up and starts going down. So how are we going to find the height of the rock at that time? We're just going to put that time back into our height function. 3 plus 135 times 135 over 32, minus 16 times that 135 over 32 squared. And of course, that's a calculator thing. And we need to remember, we should answer the question given directly, kind of translate back into rocks. So the velocity of the rock at its highest point is 0 feet per second. At that moment, the rock is 287.765625 feet above the ground. Okay, so this is not really a calculus problem, but a thinking problem. There's another time the velocity of the rock is 0. And why is that not described by the position equation above? Well, let's think about rocks. Right? So if this is time and this is position, we know this graph is going to be an inverted parabola, but you have to do a little bit of translating in that 3 plus 135t minus 16t squared, if we're not thinking about rocks, has a domain of all real numbers. And so why would the velocity be zero somewhere else? Because when the height hits zero, the equation stops being useful, right? When the height hits zero, the rock hits the ground and first period's about to start. The rock hits the ground and then maybe it bounces a little bit, but the rock has a velocity of zero from then on. Okay, so how could we figure out when the rock hits the ground? Well, is that about position, velocity, or acceleration? That is about position. So we're going to set the position equal to 0. Okay? I'm not going to do that. That's a calculator problem, but this is really about planning what to do. So let's plan a few more. Figuring out what to do, and I think that's true a lot of times in AP Calculus, figuring out what to do is the tough part. The doing it maybe isn't super easy, but is usually easier than figuring out what to do. So we're not going to, like the last couple, complete these problems. We're just going to figure out what to do. So if we have this particle moves along a line, and what that means is if we put in t equals 0, we get -8. So the particle starts at -8. If we put in 1, we get different numbers. This spits out a position. So we want to find the position of the particle when time equals 3. What do? Pretty easy. We just do 3 into this position equation. This says, what is the velocity of the particle? And notice, unlike the last, this does not say at a particular time. So this is actually asking for the first derivative of the position. So we would just write s prime of t is equal to, well, we said we weren't going to plan, but this is asking for first. We weren't going to execute. We were just going to do the plan. What about particle moving left? Is that about position, velocity, or acceleration? Well, that's kind of about position, but moving left is a change in position as the time changes. So that's about velocity. And whenever we're thinking about one-dimensional motion, we're going to have negative on the left and positive on the right. So this is about the velocity, or s prime, being negative. If we're going to find the acceleration when time equals 3, that's just going to be the second derivative, because acceleration is the derivative of velocity. Velocity is the derivative of position. We're going to do the second derivative of this position equation when time equals 3. When is the particle moving right? Okay, well, that's about velocity, and that's about velocity being positive. Ooh, particle stop. This came up before. Particle stopped is no change in position while the time is changing. So that's about velocity as well. And that's about the velocity being equal to 0. I think that's almost as straightforward as possible. What's the acceleration when time equals -3? Acceleration is the second derivative of position. And oh no, I wasn't thinking. Oh, there's an implied domain that when we're given position, velocity, and acceleration, time starts at 0, or at least the equation is only useful starting when time is equal to 0 up to some time in the future. So there's definitely a time before the simulation starts, but it's more like the equation only starts to be true at time equals 0. So displacement is kind of the weird one. And displacement's the easy one. That's just a change in position, as in the numerator of average velocity. And that would just be the position at 7 minus the position at 1. The acceleration of the particle when the velocity is 0 is kind of a two-step process. So I guess first we find the velocity. We set the velocity equal to 0. We find a time, and we put that time back into the acceleration function. Okay, so here's the one I wanted to get to. This will be the last one, so I can let the kids into first period. Total distance traveled, we understand, but I think it's the most complicated one because what we have to take into account is the sign of velocity. And so the first thing I do is find out when the velocity changes signs, and that's at time equals 2.5. We want to make sure the velocity changes signs. This leads into something else. For numbers less than 2.5, like 1, the velocity is negative, and then the velocity is positive after that. So in order to find total distance traveled, we have to treat movement in the negative direction as positive and movement in the positive direction as positive. So from time equals 1 to time equals 2.5, we get a change in position that's negative, so we put absolute value on that. And from 2.5 to 7, we get a change in position that's positive. We make that positive, and we get total distance traveled. All right. So I hope that helps. We'll leave you there, and I'm letting everybody into first period.